Hello. So some time ago, I managed to find a couple interesting features in this security system made by Paradox. And then I see Hackfest Decade coming along. It's in Canada, so I think, well, where else would I present it, since Paradox is a Canadian company? So a little bit about myself. I'm a lead researcher at Possible Security, that is Latvia, Riga. Our weather is approximately the same quality as Quebec weather, so I feel right at home. I love hacking and breaking things, and throughout my life and throughout my career, I went through different stages and different focuses. So the deepest knowledge I probably have is in network flow analysis. And so I love looking at network, I love doing live network forensics and checking stuff out. Of course, reversing isn't far from that. So then I moved on into reverse engineering, which is what this talk is about. And it is about a network in a way, right? About a bus. Then I got a bit bored, so I also moved forward into social engineering. I'm happy to see social engineering village here. Finally, was able to look at one in person in real life. A bit unconventional, I've also done some work in the legal dimension of cybersecurity, so paperwork, writing laws, and stuff like that. So I'm kind of a versatile guy. And I'm on Twitter as well, so as soon as I get back home, I will resume tweeting, so you can follow me there for updates on stuff. So the company I work for, there is one slide about that. So we do penetration testing and auditing, we do consulting and trainings, and we also, of course, solve hard problems, and we do reverse engineering. Even though this presentation is not related to the company, I just want to say thanks to them for paying for half of my travel here, even though this presentation is not endorsed or connected with them. So we're going to have a live demo as well. So that will be exciting. I always try to do live demos, even though they sometimes fail. I've learned if you test them 3 times, there's 90% chance it's going to work. So I hope it really works. And the goal of the presentation today, the structure that I built into the presentation, I chose it so that you can not only recreate the research I've done, but also reapply this to other devices. So if there are any potential reverse engineers out there who would like to try out this new field, I try to include as much detail as possible so you can actually do this on an unknown system and try to take a look at it. Not only security system, any kind of closed source system as a communication bus. So let's jump right in. As I said, it's a Canadian company, Paradox Security Systems. They are founded in 1989, and they make modular security alarms. How many of you have not heard of Paradox Security Systems? About a half. OK. And maybe some of you have that at home or at work? OK, like 20%, OK. So don't hack it unless it's yours and unless a security company agrees. Right, so what's important to this talk is that they make 3 kinds of security systems. So the basic kind is Spectra, and it's expandable security systems. So you get your setup, you can plug modules, you can protect doors, you can protect windows, and so on. But that's it, basically. I mean, it's OK, it works, it does everything it needs, so you can do anything with any of these. Then there is Evo. And Evo, Magellan, it's marketed as high security and access system. So it provides higher security. It's meant for, as I say, banks and places like that. You can integrate it with a RFID reader and so on. And then we have the third one, Magellan, which is wireless security system, which is basically a combination of the two in wireless. So if you don't want to ruin your new flat or new house with wires, you just install these wireless sensors, supposedly very secure, and then you can work from there. So I want to do a shout out to 2 guys that have done some prior research on the topic. So there was some research on working, some research on interfacing with via COMBUS, but for the Spectre series, so for the less secure one. It was done by Martin Horizonov, so you can check that out if you like. The code he supplied is partially working, and I recently checked, and he moved on to working with Serial instead of COMBUS, actually. And then for Magellan, people are working with serial port. We will take a look at what that is exactly and what's the difference. So it's all over the place, people asking, how do I get data from my Paradox system? How do I connect to it? And some people answering. There are also leaked documents. I mean, it's nothing secret. I think it's commercial, and if you sign an NDA, you can get them, and then you also have them just lying around online, some PDFs for the serial port. So that's something we can use. And Gytis Ramanauskis, who's from Lithuania, which is not Latvia, but a neighboring country, also has published some code on GitHub. But once again, this is for serial port, which is less interesting for what we're doing here. Now, of course, I did follow responsible disclosure process as well, and this is how it went. I know that some of you here in the audience have also tried responsible disclosing to this company. So at first, I wrote an email to their support email address, right? And what I get basically is, of course, if you do responsible disclosure, you don't start just by saying, hey, this is a detail, right? You start by establishing proper contact. So I just write, hey, I found some security issue. I need to talk with someone. And what I got couple days later is, well, we're not sure you really found anything, and just write us what you have to the support email address. So we bounce back and forth, and I'll try to get proper contact for security. So I get a feeling that they don't really have a process in place. Finally, to the same support email address, I do send out that, well, this is a general description of how it works, and we're going to see it on this level here today. Even I'm actually going to go more technical than the email that I sent to them. And what I got back was basically, well, thanks, the information has been dealt with. I didn't even send them a proof of concept. I didn't even describe it on a low enough level. But yeah, it's dealt with. And then I tried to follow up, and what I got was, well, for obvious security reasons, it is our policy to never discuss engineering matters, blah, 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 blah. We will not be commenting. So I thought, OK, it's been dealt with, no comment. So just to be sure, I gave them a couple of years, and now I'm in Canada. I hope a couple of years was enough to fix it. So there we go. OK, let's look at the components. So this is one of the motherboards, I call them, the master panel, right? It's a modular system, all of them. This is for Spectra series. Well, usually how it goes is you don't buy those. You hire a security company, and they buy all those devices and come to your home or office and set everything up. So this is the main brain of the system. We also have some ancillaries, like battery, power supply, siren, and stuff like that, which is not really interesting. Usually 2 wires, transmits a lot of current, don't want to screw with that. Then we have slaves on the COMBUS. And these include a wide array of different things. Keypads, of course, I have one right here. Then modules, including expansion modules if you want to add something more that you can add to your original module. Let's say you bought this chip and Spectra device and you want something more, you can buy expansion module and convert it into something better. There's a printer module. That's the one displayed here. You see a parallel port, a serial port, and a USB port. So you can connect your printer even if it's a modern one. Listening modules, which is kind of nice way of saying spying on what people are talking in your house. So different tools that actually use COMBUS to communicate. Then we have zone devices. And all they do is they provide input to the panel. They simply send an interrupt in a very simplistic way. So it's simply change of resistance on the wire. We have magnetic sensors that you can install on doors of windows. We have passive infrared sensors that we can use for movement detection. We have panic buttons and stuff like that. So anything that can be easily interrupted. It's only for input. Then we also have some wiring available only for output, so programmable outputs. And they can drive up to 1/10 of an ampere. It's a solid-state relay, and we can add like a light bulb, like a fan, or close a door physically, anything we want. And then finally, there are serial devices which you can connect to the serial port. So we have serial converters. So the protocol on serial port here is RS485. We have serial converters to actually get it into something that most computers can speak to, like USB or RS-232. We have IP modules, which allows you to connect your great system online, and then people can access it via an IP address. GSM modules to do the same over the mobile connection. So that's a quick overview of how the system works. Well, not how it works, but the components. Let's look deeper now. So this is EVO 192 panel of the secure series and the most advanced one available. That is the one I have here with me today. This is how it looks. And well, what can we see here? We have our power, right? We have supply, alternating current, 16.5 volts. We have battery in case current goes down, because burglars sometimes just cut off your power and then they get in. So of course we need to have battery, and we also have a 3-volt battery so that you don't have to reset the clock every time the panel runs out of both the AC input and the DC battery, which is unlikely, but there you have it. On many panels, this actually isn't installed. So then we have the COMBUS, which is what this talk is about. And COMBUS consists of these 4 wires here, which is plus, minus, green, and yellow. This is how they're called. And this one is called service keypad, which is basically just the same 4 wires, which an installer can come to your house and plug into your panel and not have to run between the panel, where the panel is, and the keypad. And we have other ports, as I already mentioned. We have a serial port right here. We have the mem key port, which I think warrants some further investigation. So this is basically a port where you plug in a special, let's call it a USB drive. But on one side of the drive, you have connectors that go into this kind of slot. And it copies the configuration, or it writes the configuration from the USB drive to the panel, which is kind of cool. And then we have these 2 connectors for voice dialer, in case someone still uses that. So the reverse engineering process. How did I do it? So the tools I used is a logic analyzer. Well, I actually did use an oscilloscope at first, so this is a simplified version. But anyway, a logic analyzer and Arduino, which is quite a universal tool that you can use up to a specific frequency. Of course, actually, when I was reviewing my slides on the flight from Frankfurt to Toronto, the lady sitting next to me said, "Oh, Arduino, I know that." So I was excited. Wow, you know Arduino? How so? And she was from Italy. Apparently, that's some guy's name. So this is what I came up with. I'm a huge fan of networking leveling, like DoD model or ISO model, right? And this is what I came up with. Probably they have some internal documents where they have their own layers. These are my layers, which you're free to use, of course. This is how I look at the traffic to make it more recognizable. This is how COMBUS is built on an electrical level. So we have a master device, which is the panel, and then we can have a number of slave devices. I don't recall the specific number. It's quite a lot. It's 3 digits, I think. So that's it. You can't have 2 master devices. That's a gist of the graphic on the left here. On the right, so I was able to divide COMBUS into multiple layers of, let's call it encoding. So electrical, when we look at electrical specs, signal, packet, command, and payload. Now, for those of you here or at home who will try to use this presentation to reverse engineer something new, I find it easier to just look at the stuff first. The next slides are going to describe that. And this I created later, so for reference to go back to it. It's hard to start with creating this part and then doing the next slides. OK, so let's look at the electrical layer then. You see a keypad on the right. That's a keypad like this. If you turn it around, you see on the back, you'll see a couple of connectors where you can connect some wires. And if it's an installed system, then you will see that some of the wires are connected, at least the first 4 ones, yellow, green, black, and red, and maybe the blue one as well. So PGM would not usually be connected, but it may be. So the question is, let's say you are on an abandoned island and all you have is this nuclear reactor and you don't have any internet, right? So how do you go and try to understand what's happening there without using any docs. So you look at the colors, and those are the actual labels used on the device, on the keypad, right? So it doesn't really say what yellow or green is, even though black and red is set as plus and minus on the board, right, on the panel. Well, in any case, looking just at the keypad, we see there's this wire coming in with 4 wires in here and connecting somewhere. So that's the COMBUS, obviously, 4-wire bus. So we have to look at those 4 wires. So what can we do then? Black is a good guess for ground, right? So we just find a ground connection on the board somewhere, connect to black, measure resistance. In case resistance is 0, we found the ground. If not, we try a different one, like yellow, green, whatever, until we find it. So we have ground, so that's happy. Then let's take a look at the red one, which is usually used for providing power, right? So we connect again our probes to black and red, and we measure the voltage on there. So there is stable DC voltage there. So red is obviously power. So great, we shouldn't be connecting any sensitive electronics to those. We have yellow and green remaining, so we connect our probes there, and it's kind of fluctuating, and we don't see anything good. So that's when we need to go to the signal layer. Because we did everything we could electrically, now we have to take a look at the signal. The graph on the bottom is actually what you get when connecting like digital signal analyzer, like Solovjovs, for example. And we can see from here that the yellow, which is on the bottom, is super symmetric. It goes up and down, up and down, up and down. And the green one on the top is not. So by my experience, it's apparent that yellow is a clock, which is provided by the panel, and green is data, because you can't really encode too much data in a signal like that, right? You would, well, that would be useless. So what else can we see from this step here? We have 40 milliseconds from here to here between packet bursts. So that's going to come of use. And 1 clock cycle is 1 millisecond, which means mathematically that signal is 1 kilohertz, which we get, again, from here. If we zoom in a bit better, we can actually see that it is indeed 1 millisecond for the clock to go up, down, and back to the start point. So that's the signal layer. But we still need to understand how encoding works. Here, I zoomed in on one of the short packets here from beginning to the end. And the question is, what's there? Well, the easiest thing to do, right, any person with an engineering background or background in computing would, of course, see, OK, so if we take a look here, if clock is high, the yellow is a clock. If clock is high, then data is always 1. So it doesn't carry anything, right? We take this green one, it's always green, 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 green. Every time the clock is high, it's 1. So it's probably redundant. So we just assume that if clock is low, then that's data. So when clock is red, 0, then we have data on here. So red, so OK. We write it in. That's how it looks like. That is how it looks like. We get some info, which is actually not bad. This is actually an actual command, 0C912D21, which is what we get if you convert it to hex. But the thing is, we should have two-way communications, right? We have a keypad here that's connected to the COMBUS. I mean, it is showing what's happening to the system, right? If anything is open, any zones, or if there are any troubles or alarms. But at the same time, I can type stuff here. And it should communicate back to the panel. So the question is, how is it happening? And, well, apparently, something is missing here. So the correct answer, after looking at it for an hour or two, is that the clock is actually used to discern communication direction. So when clock is high, slave is talking, and when clock is low, master is talking, right? We had clock is low here. That's the master's message. But clock is high is slave's message. And how it works on electrical level is that slave pulls down the voltage to send 1. So what we actually had here is, for these ones, that is slave saying nothing. Slave sending all zeros, not communicating at all. So that's how it works. We have master, slave, master, slave, master, slave. Here we have nothing, right? And here at the beginning, the first byte, first 8 bits are not used by the slave. I don't know why. Probably in case the cable is really long, so or the system is super slow, so the slave can get ready to send their message. So the hardware setup, I have it set up right here. And how do I set it up to be able to distinguish? So far, I've been working with the logic analyzer, meaning that I would, well, need to write some funky script to actually analyze that, but I want to do it properly. I want to have software running. I want to do it in Python, let's say. So this is the hardware setup that I created for reading only. It's not going to work because of how it's set up. Not going to work for writing, but you can also do that, and then you can have even more fun. So I have ground connected to the black wire. Well, black wire connected to ground on my Arduino. Green wire connected to pin 12, which is just the pin I chose, and the yellow is connected to pin 8. And yellow was, of course, the clock, right? So, and the signal is 12 volts, so that's something to keep in mind when choosing the resistances, right? I have 5-volt Arduino here, so I add some resistors, a super low one on the ground just to prevent interference with the panel, and higher ones on the actual data and clock wires. And this is basically how it goes. This slide here just takes everything I just talked about for the last 5 minutes and puts it into a nice pseudocode, right? When clock changes, we wait 50 microseconds just in case the clock is a bit ahead of the actual data, right? Remember, it's 1 millisecond per clock cycle. So we wait 50 microseconds. If clock is high, we save the new byte on data pin to master. And we shift master to the left, so we can actually save all the data there. If clock is low, then we save the inverted byte on the data pin to the slave. And in case it has been idle for more than 2 milliseconds, which is 2 clock cycles, then we check if we have any data, and if we have, we return it via USB, and we reset the internal variables. That's it. So super simple. That's what I have running on this Arduino here, and that means I can actually use this USB cable to connect to this system. Now let's take a look at packet structure. So there are 3 common lengths of the packets, but that's not all. It really depends on the command that you're sending. So one of the commands that you can send is the result command, where the panel communicates back to a COMBUS slave device the result of the action requested. So the first byte from the master is the command. So there can be up to 256 commands. We have checksum right here. We can talk about that a bit later. And the last one is unused. It's always, well, it's sometimes zeros. It's sometimes 1F. It's sometimes something strange. I guess it's some electrical problem there. But it's unused by the system, so wisely done. Then we have a different command here, which is an event command. And as you can see, it's shorter. It still has a checksum here. And the last one is unused. And then we have the super short one, which is a heartbeat command. And it's only 4 bytes. It has no checksum. And for the slave, then, some examples. For the slave, the first byte is unused because, I don't know why, because it's just waiting. So we have this unused here, and the first one is unused there. Then we have channel requests. So the second bit from the right of the second byte is set high. That way, the devices on the bus know that the device wants to transmit. And then we have a command again. This is authorize user command or enter code command. And we have some parameters there, checksum at the end. And here is a different command where it usually starts with this one, right? If slave isn't communicate, then you start typing something, you will see this one which says, I want to talk, I have nothing to say. So just request the channel for themselves. So those are some examples of packet structures. And checksum is super easy. Just the sum, of course, module is 256. The important part is what is in the sum. So the sum contains everything from the orange byte up to before the green byte here. So in this case, it doesn't include the 0, 2, and 0, 0 in there, in case you want to look into that. Now, before we do the demo, just 2 commands. The command level to actually show you how they're built. This is a heartbeat or clock command. Its code is either C or D sometimes. And then it has a sequence number. So every command, every unique command sent from the panel, it's sent by the panel, by the way, is going to have a sequence number from 0 to 255 and then back to 0. And the last bit of the sequence number will decide the payload. If it's going to be day of the month and hour, or it's going to be minutes and seconds, depending on the last bit. Now, command for code entry, this is sent by the keypad, as you can see from 0002 at the beginning. UT is user type. It is, so the first bit, if it's set to 1, it's a programmer. If it's not set to 1, it's a normal user. Programmer is the guy who comes to your house and they have this 6-digit code instead of 4-digit code that they can change all the system. CT is the code type. Nothing much to say. I think FF and 01 or 02 is what I've seen. It depends on what kind of code is being typed in. So a programmer will have a different type of code. Then we have the code itself. I think it allows up to 12 characters there, right? In this case, it's a 4-character code. And then we have serial number of source device. So that tells me we also have no proper authentication of the client. You can just spoof the serial number. And it also matches the actual serial number on the device, which is cool. And we have the checksum, of course, as discussed previously. And so the payloads. What did I understand about the payloads? There is no encryption used. So it's all in plain text. Text is usually fixed length. Often it's 16 characters, and it's filled by spaces, right? We can see an example here. This is a full packet. Oops. This is a full packet. We can see the type of the packet, right? We can see the string starting here. So it's door 1. There's a space. There is some numbers and more spaces. So this is a packet that is sent when system boots up. It actually sends all the information about all the zones and all the names that you have on the panels, so that all the panels also know that. And numbers are usually packed binary coded decimals. So meaning if you want to send, let's say, 11, instead of sending 0A, you send 11. So in hex. And to obfuscate it, so zeros are not sent as zeros, but as A's. So that's all the security they have. So at least we got obfuscation, even though we don't have encryption. OK, then. Let's do a demo, which is what some of you came here for, I guess. Right, so the user manual, installer manual, the one that's leaked online, says that before connecting a module to the COMBUS, remove AC and battery power from the control panel. Well, we don't have time for that, so we're not going to do that. Right. So I just launched a terminal application that simply is reading what's on the wire. And we see a bunch of zeros. We might see some other data because the wires are just dangling right now. And what an attacker or researcher may do, right? So you have this keypad here. You have wire going to the keypad. What you can do is you can cut the wire open. Not disturbing anything. You cut the wire open. You will see multiple wires. In this case, it's more than 4, but we know the colors used, right? And you can try to remove isolation. Try to remove the plastic from some of the wires. And then when you've done that, you can connect to the wires without disturbing anything. So let's try doing just that. I'll start with ground. So we were supposed to have a small camera for this super small thing, but we don't. Sorry about that. It's not going to take long. So we connect the ground. Then we can connect the clock, which is the yellow one. And then we can connect the data, which is the green one. Right, so we see some data. We actually see the heartbeat packets right here, and we see the zeros that are going back from the slaves. OK, so that's not fun to watch. Let's try to interpret that. If we now launch the decoder, we can actually see the packets decoded, right? We can see that one packet is sending the day of month, which is 2nd of November, and an hour, which is 16, which means I still have around 15 minutes. And the second packet is actually sending hour, minute and the second. And we can see the sequence number just rotated through 2055 to 0. So, well, that's what's happening there. I will now remove these filter. I will now filter these packets so that, so that we see what we actually want to see, right? Now let me clear the screen. OK, so now I've filtered these time packets. Ignore the COM error. And now we can, for example, let's say we open a door, right? If you open a door, we see that a packet was sent, it's already decoded here. Zone 1 is opened in area 1, CRC is OK. There are troubles currently on the system, and that's the timestamp of the event, right? We have a movement, for example, on some passive infrared sensor. Again, zone is open. And then door gets closed, and then let's say passive infrared sensor also registers no movement anymore. So we can decode that quite nicely and neatly. OK, now what happens if, let's say, as we are connected here, I type in a code, right? Let's say I want to arm the system with the code 1234. OK, so it's showing me code denied over there. We also see the same here. We see the serial number, which I removed some symbols from it. We see the code entered, and we see the panel speaking back saying that it was denied, right? If we knew the right code, we could, of course, see it. The important part here is that the attacker on this position can not only see what's being tapped on the keypad, but also 100% understand if the code is correct or not. OK, let's say that this keypad is somewhere far away and no one uses it. It's just gathering dust, right? And no one will ever come there. What happens if attacker sets up over there and then real keypad is used somewhere else? So let's say there's a real keypad here. I'm gonna arm the system with instant arm, and it asks me for my code. I'm gonna enter the code. Oops, wrong code. Now, there we go. Now, what happened is, of course, we see that code is this, and the result was accepted. But also important is because of how COMBUS is built, this part here also receives what we're typing on different keypad, which is a huge thing, I think. Well, it's now arming. I think it's going to take like 35 more seconds to arm. But one last thing I want to show in the demo is a remote, right? They also make these remotes where you can just press a button and you don't have to enter any codes, and you can nicely control your stuff from away, right? I can press the info button, for example, on the remote here. And if I press the info button on the remote, it also gets broadcast over this wired COMBUS, even though it's not directly connected to COMBUS, but just for the panel. So we can see that info button was pressed on the remote, which was sent out by the slave, and then also confirmed by the panel. And we have an event here, blah, blah, blah. OK, what happened here? Arming finally happened. So 1 minute passed. Arming happened. We see that arming with no delay was used, special arm partial, so it's partially armed, and user 4 was the one that armed the area. Now I can just press this button here, and disarm the panel using a master code. Looking into this would be fun, right? Looking at the radio codes used for this, actually. I think that might also, seeing what we see here, that might also bring us some interesting stuff. OK, so that's the end for the demo. We can return to it in questions, in where we have questions later on if you want. Let's continue. So, this is what their webpage said this week. Yeah. Well, I don't know what they mean by high security, but okay then. Some scenarios. How can this be used, in fact? Of course, I hope all of you noticed that this attack requires physical access to COMBUS, right? It's not a radio attack. So one scenario I call the warehouse attack. These systems are also used in warehouses, large storage areas with multiple entries, right? I was going to Tallinn, which is the capital of Estonia, neighboring country of Latvia, once, and I had to choose a hotel. And they had this hotel that was used for the Olympics a couple tens of years ago. And I thought, wow, that's cool. It was built. It was not only used, it was built for the Olympics. I'd love to stay in a Soviet hotel. No sarcasm, because I mean, Latvia has moved quite high up from Soviet times. So I thought, well, I'd like to experience that. So there's a Soviet hotel. Everything is expected. But it's huge. It's like 1 kilometer in length. And the entry is only from one side. So for buildings like that, you usually have entries from multiple sides, and then you have keypads on all the entries. Well, some of the keypads tend to get abandoned. Let's say there is reconstruction going at one of the ends, and no one's going in there. Or just, let's say that parking was built at near one entry or near two of the entries, and third one is left unattended. So attacker can easily pull this from the wall, connect to the wires, and attach a much smaller device than this. You can actually build it, well, not exactly in a wire, but quite small, and leave it there. And then when a different keypad is used somewhere else, the attacker will still get the right codes. The second thing you can do, if you make sure that you can actually write to the bus, is you can brute force the pin codes, which is 4 digits. We have lockout configured, but you can easily brute force couple pins an hour, right? And again, if you are in for the long game, you can simply check out all the pins and you can unlock it yourself. So let's say the system, let's say it's a secret site that's, as the ad said, a secret military site that's only used in case of war, no one's there. You connect to it, you do your stuff, and you get the code. So in summary, the results. I was able to build the hardware needed and decoding software for that. So it's going to be published. So the implication here is that you will be able to do that yourself. You will take a look at that. And I really hope that these problems are fixed. And because I deliberately tried to get an old system for the demo. I should actually buy a new one and see if it still works. I really hope it doesn't. But then again, seeing that they have not announced any replacements for several parts, for separate parts of the system, right, for keypads or panels, and they are still interoperable in between, I would doubt that our update has actually been pushed out. The protocol is partially transcribed. You can actually see much more than we saw in the demo there. All the events. We can see all the events. We can see different codes being entered. We can see partitioning happening when the system boots up. It takes like around 1 to 3 minutes when the system starts. What's actually happening is your panel is communicating via COMBUS to all the devices, enumerating them, and then sending back all the devices to all the other devices, so everyone knows what's where. And the system is built on such a principle that every COMBUS device has memory that stores the information for that particular boot up. So it's not rebroadcast every time. For example, the year is stored when the system boots up, or when the date is changed. Same with COMBUS components, right? Panel just informs all the keypads and all the other devices, and that's it. And they have to remember that. So since protocol is partially transcribed, you can take a look at it. You can play with it, you can work with your own systems, and you can interface with them. You can make connections with different modules of your own. Well, and possible attacks, of course, all I can say is I hope it's fixed, right? Because this is not a radio attack, but that's probably coming in a year or so. Solutions I'd suggest. So, of course, first thing is encryption at the command layer. So you would need to encrypt the command layer. You would, that's the basic thing for a high security system. TLS might be used with the processing power of today's communications, which also has added advantage of enabling mutual slave-master authentication. One attack that I didn't talk about today is the possibility to spoof a slave device on COMBUS, because all we have is the serial number, right? It's similar to network layer in a classical network, right? We have a MAC address, we can simply spoof it if that's all we have, and we see it, spoof it. So that's a bit problematic. So client certificates might be used. That's probably not the best idea, but I mean, if the systems are powerful enough, we can go that way. But we still need mutual authentication. And sensitive payload should be encrypted at the payload level. So pin code should not be sent. When you type 7007, you should not see 7AA7 on the bus. My idea for this is unique per panel key. So panel, when installer installs it, generates a key, or the key is typed in, and all the devices then store the key permanently, and they can encrypt it. Or maybe they just send the key out on panel boot up, which happens quite rarely. So further research that we should look into. I will be looking into some of that. If you're interested in looking at some of that, just go ahead and do it. Find me on GitHub, and then we can maybe cooperate. Or you can do it on your own. You don't have to report to me or anything. So anti-collision protocol is something I'd like to look into. So there are multiple devices on the COMBUS, multiple slave devices. What happens if multiple devices want to send at the same time? So that's something I'm interested in. Denial of service attacks. Can we use COMBUS to make the panel not work at all? That might be nice. We just come to a keypad, we shut down the panel, and we're good. Emulating a slave, of course, writing to the bus would be important. COMBUS over radio. So remember those Magellan panels? They use radio frequencies, and keypads communicate via COMBUS. So I haven't looked into it, but my fear is that, well, they just took COMBUS and put it over RF. That would be kind of bad, since they don't encrypt it, at least here. Then RF attacks, which I already mentioned, right? We have these remotes, which might be used to disarm the system. Maybe there are some holes there. And firmware reverse engineering is another topic, which is something I mastered on a professional level only in the recent year. And I'd like to dump the firmware and take a look at what's in there and actually take a look at the instructions and opcodes there. And of course, we have to think about logo for that. So I think we need one. I created one. Maybe it works. Right. So with that, the resources, here are the addresses and the respective dates when stuff will be available. Slides will be available today, but I don't have access to my stuff from here, so I'll be back, and then I'll upload the slides, and tools will be also available soon after that. I'll give you a second to write all that down, but yeah, that's it, and thank you very much for listening.